Welcome to the lecture on addition and elimination reactions, part 4. And this module deals with Aldol condensation, Claisen condensation, and Dieckmann condensation. Aldol condensation is the coupling reaction of an enolate ion or enolizable carbanion with a carbonyl compound to form a beta hydroxy carbonyl. And this beta hydroxy carbonyl compound may sometimes undergo dehydration to give a conjugated enone, which we call as alpha beta unsaturated carbonyl. So in aldol condensation, we start with an aldehyde or ketone which has got an alpha hydrogen. So this is carbonyl carbon and this is alpha carbon. So the hydrogen atoms present in alpha carbon are called alpha hydrogen atoms. These hydrogen atoms are acidic because once a H plus ion is removed from here, we get a carbanion here, and this carbanion, the minus charge, can move here to make a double bond, and this double bond will dissociate to give O minus. So a double bond here and a single bond O minus, that is what we call as enolate ion. Or after the removal of H plus ion, we have a minus. So this carbanion is called enolizable carbanion. So an aldehyde or ketone with alpha hydrogen, when treated with a base, the base removes an alpha hydrogen, generating a carbanion which is enolizable. And once it becomes enolate, it can once again become carbanion. There is a resonance between the enolizable carbanion and enolate. So this enolate ion reacts with another carbonyl compound which may be an aldehyde or ketone. The carbanion attacks at the carbonyl compound, therefore it makes a bond here, and this pi bond between carbon and oxygen will break to give O minus, and it will take up a proton from the solvent to form this OH. So this is the carbonyl group and this is the carbonyl part, and this is the enolizable carbanion, alpha carbon of the carbonyl. Enolizable carbanion attacked the carbonyl carbon of another compound, resulting in beta hydroxy carbonyl. This is carbonyl and this is alpha carbon and this is beta. So beta hydroxy carbonyl compound, and this is what we call as aldol. And this reaction on heating with acid or by E2 mechanism with bases can undergo dehydration to form a double bond here. So this beta hydroxy carbonyl compound in acidic medium will follow E1 mechanism for elimination of water to make a double bond. And if you add a strong base, it will undergo E2 elimination to make a double bond here. So in acidic medium, E1 reaction operates here. With a strong base, E2 elimination operates here to form a alpha beta unsaturated carbonyl or conjugated enone. The mechanism of the reaction is one aldehyde or ketone is treated with a base. The base removes the most acidic hydrogen of the carbonyl compound, the alpha hydrogen. The base abstracts alpha hydrogen, resulting in the formation of a carbanion here, that is enolizable. So when the minus goes here, it makes a double bond and the pi bond breaks to give O minus. This is enolate. So the enolizable carbanion is converted to enolate ion, and this enolate ion reacts with another carbonyl compound which may be an aldehyde or ketone. The minus comes back here, pushing this double bond to carbon. Once again the carbanion is generated. That carbanion attacks carbonyl carbon. When a new bond is made, and this is broken to give O minus. So the two different molecules are condensed. One carbonyl is condensed with another carbonyl, and that is why we call this condensation. These two are coupled with one another. And after condensation, this medium we add an acid. We call it as acidic workup. So with the acid, the O minus gets a proton. So we end up with beta hydroxy carbonyl alpha beta hydroxy carbonyl. So when we add a strong acid and heat it, the OH will get protonated and it will go out as water, resulting in carbocation, and that will be followed by deprotonation to form a double bond here. And we can do dehydration with strong bases by E2 reaction also. So this is Aldol condensation. One carbonyl reacts with alpha hydrogen, reacts with another aldehyde or ketone, ending up with beta hydroxy carbonyl, and it may be dehydrated to alpha beta unsaturated carbonyl compound, either with acids or with base. In the mechanism we discussed, there are three stages. In the first step, a base removes an alpha hydrogen from an aldehyde or ketone with alpha hydrogen, resulting in the formation of enolizable carbanion, and it is converted to enolate ion. That is the first step. And that enolate ion reacts with another carbonyl compound, resulting in the formation of beta hydroxy aldehyde or ketone, and that is called an aldol. Beta hydroxy carbonyl, hydroxy we represent with all. Aldehyde or ketone, in general we write aldol. Carbonyl with OH. So beta hydroxy aldehyde or ketone is called an aldol. And this aldol, on dehydration we get an alpha beta unsaturated carbonyl compound. So the mechanism we discussed is a base promoted mechanism, and this reaction is possible with the acids also. In acid catalyzed aldol condensation, the aldehyde or ketone with alpha hydrogen is treated with an acid. So this acid protonates this carbonyl oxygen. Once it is protonated, it undergoes resonance to form an enol. So the carbonyl compound with alpha hydrogen is treated with an acid. It gets protonated. Once it is protonated, it is forming its resonance structure, that is enol. And this enol reacts with another aldehyde or ketone in acidic medium, that is also in protonated form. Once it is protonated, the carbonyl carbon becomes more electrophilic. Therefore, it readily reacts even with weak nucleophile. So this enol has a OH here. The lone pair of oxygen come here to make a double bond, and this double bond breaks to give a minus. That minus attacks the electrophilic carbon here, and this bond is shifted to the protonated oxygen, and that is how we end up with a beta hydroxy carbonyl. In the same acidic environment, this OH is protonated Once it is protonated, it is removed as a water molecule, resulting in the formation of carbocation. And once a carbocation is generated here, a H plus from the adjacent carbon is removed as proton. It is called deprotonation. So the carbocation undergoes a deprotonation to make a double bond here, that is alpha beta unsaturated carbonyl, and this is acid catalyzed aldol condensation followed by dehydration. Here are some examples for aldol condensation reactions. So here I have taken butanaldehyde. So one butanaldehyde molecule generates enolate, and that reacts with another butanaldehyde molecule to form a beta hydroxy carbonyl. So two butanaldehyde molecules condense together in basic medium to form a beta hydroxy carbonyl compound, and with the strong base. So here you have carbonyl group, and this is alpha carbon. We know alpha hydrogens are acidic. So the strong base removes the acidic hydrogen from here, resulting in formation of carbanion. That minus will make a bond here and will push out the OH minus. So the hydroxide base removes alpha hydrogen, generating carbanion, and this carbanion is pushing out a hydroxide. But these two steps are taking place simultaneously and in a single step, and that is what we call as bimolecular elimination mechanism, E2 mechanism, that results in the formation of alpha beta unsaturated carbonyl compound. Here again I have given another aldehyde. In strong basic medium, it undergoes condensation to form a beta hydroxy carbonyl followed by dehydration to give alpha beta unsaturated carbonyl or conjugated enone. Normally in aldol condensation we prefer only aldehydes. Ketones are less reactive electrophiles than aldehydes. Therefore, for aldol condensation, ketones are very often not used. And similarly, we don't use mixture of aldehydes. So one aldehyde reacting with another different aldehyde is not usually carried out because mixed aldol condensation resulting in the formation of several products, and the separation of them will be very difficult. So mixed aldol condensations and aldol condensations with ketones are not preferred usually. Aldol condensation is a carbon-carbon bond forming reaction. Similarly, Claisen condensation is also a carbon-carbon bond forming reaction. In aldol condensation, it was condensation between aldehydes or ketones, but here Claisen condensation is a carbon-carbon bond forming reaction which occurs between two esters in the presence of sodium alkoxide as a base. In aldol condensation we use hydroxide as a base, but here in Claisen condensation we do not use hydroxide, instead we use alkoxide. The reason is the Claisen condensation results in the formation of a beta keto ester. If we use hydroxide base, that will hydrolyze this ester product. Therefore, we don't use hydroxide bases, instead we use sodium alkoxide. So in Claisen condensation, it is a condensation reaction taking place between two esters. So with ester, with alpha hydrogen, we add sodium alkoxide, This sodium alkoxide generates carbanion in the alpha position of carbonyl group. It is very similar to the first step of aldol condensation, generation of enolate, and that reacts with another ester molecule resulting in the formation of beta keto ester. To explain the mechanism of Claisen condensation, I have taken ethyl acetate as an example. Ethyl acetate, one molecule of ethyl acetate reacts with sodium ethoxide base. So with ethyl acetate we add sodium alkoxide base. The alkoxide base removes the most acidic hydrogen from alpha carbon. So ethoxide removes the most acidic hydrogen, resulting in the formation of enolate ion. This is exactly the first step of aldol condensation, removal of alpha hydrogen by a base. And this enolate ion is reacting with another ester molecule. So the minus comes back, resulting in the formation of carbanion. C minus attacks here, generating O minus. This O minus comes back, pushing out the ethoxide out. Once the ethoxide is removed, we get acetoacetic ester, ethyl acetoacetate. So this is a good example for Claisen condensation, where two ester molecules are condensed to give the beta keto ester. Therefore, the Claisen reaction involves two steps. The first step is the formation of enolate ion by the abstraction of alpha hydrogen by an alkoxide base. And this is exactly the first step of aldol condensation. The only difference is in aldol condensation we use hydroxide base. In Claisen condensation we use alkoxide base. The second step is the resulting enolate ion is attacking the carbonyl carbon of the ester molecule, another ester molecule. So therefore, a nucleophile attacks at carbonyl carbon, causing a substitution at carbonyl carbon. So the alkoxide group that is already present in the ester is replaced by the enolate ion. That results in the formation of a beta keto ester. One more example I have given here by taking methyl proponovate. So it is methyl ester of propanoic acid. With this we add sodium methoxide base. This methoxide base removes the alpha hydrogen, the most acidic hydrogen of this ester, resulting in the formation of carbanion. This is the carbanion, this is the enolizable carbanion, it can form enolate. And this is the first step. Then in the next step, this enolizable carbanion attacks the carbonyl carbon of another ester, resulting in an intermediate where this minus comes back, pushing out the alkoxide. So alkoxide, the leaving group, gets away, resulting in the formation of a new carbonyl. Therefore, in an ester, we have removed the alpha hydrogen by another acyl group. A new carbonyl group has joined here. So a H plus from here is removed and a carbonyl is added. So this is the Claisen condensation of methyl proponovate. A successful Claisen condensation requires an ester with alpha hydrogen and an equivalent amount of a base, not catalytic amount of base. So if you use 1 mole of ester, there should be 1 mole of base. So an equivalent amount of base should be used. and then we should add an acid to protonate the beta keto ester anion. So the acid that we add will protonate the alkoxide ion that could cause the reaction to reverse. So any alkoxide ion that is expelled from the ester will also be protonated, therefore the reaction will not go in the reverse direction. Therefore, in a Claisen condensation, we need an ester with alpha hydrogen and equivalent amount of base, and we should add an acid to protonate the beta keto ester anion, and the alkoxide ion that is expelled from this ester. Therefore, the reaction is not going in the reverse direction. One more example I have given here for the Claisen condensation reaction. The Claisen condensation between mixture of esters is called crossed Claisen condensation. So here we use different esters as reactants, and usually we don't prefer this crossed Claisen condensation because we get a complex mixture as a product. So we get mixture of products, so separation of those products will be difficult. Therefore we usually avoid this kind of mixed Claisen condensation. So in this case there is no alpha hydrogen in this ester, therefore this is okay, because carbanion, enolizable carbanion will be generated only from this ester, and that will attack the ester without alpha hydrogen. So mixed Claisen condensation between two esters, one with alpha hydrogen, another without alpha hydrogen, is okay. Suppose if both the esters are having alpha hydrogen, we will end up with a mixture of products, and that is not a preferable reaction or preferable strategy for forming a product. Dieckmann reaction or Dieckmann condensation is an intramolecular Claisen condensation, and in this intramolecular Claisen condensation the reactant is a diester, and when we add an alkoxide here, it removes an alpha hydrogen from one of the alpha carbon atoms of the ester. So for this ester part this is alpha hydrogen, and for this ester part this is alpha hydrogen. So any one of the alpha hydrogen is removed, resulting in the formation of enolizable carbanion, and that carbanion will attack. Suppose if this alpha hydrogen is removed by alkoxide, we get carbanion here, and that carbanion attacks this carbonyl group. A nucleophilic substitution takes place at this carbonyl carbon, pushing this alkoxide out. So carbanion makes a bond with this carbon, pushing this bond out to form O minus. O minus comes back, pushing this methoxide. So that results in the formation of a cyclic beta keto ester. So Dieckmann reaction is an intramolecular Claisen condensation. The reactant molecule has got two ester parts, both containing alpha hydrogens. With that we add an alkoxide base that generates an enolizable carbanion that attacks another carbonyl carbon, pushing the alkoxide, resulting in beta keto ester, cyclic beta keto ester, and this is Dieckmann condensation. Once again I have explained the mechanism of the reaction. So this is the diester, we add a base, the base removes alpha hydrogen from any one of the two alpha carbon atoms, resulting in the formation of an enolizable carbon ion attacks this carbon, pushing this bond out. O minus comes back, pushing this alkoxide. We end up with beta keto cyclic ester. All the three reactions we discussed in this module are carbon-carbon bond forming reactions. Therefore, all the three are important. Thank you.